Okay, welcome Year 12. This is something we normally teach much earlier in the year, but it's very hands-on. So, 2 chapters on electricity. The first one is about what happens inside circuits, so the basic level of understanding, making sure we know where electricity is flowing and so on, for which we're going to use a really kind of powerful model. I think works really helpfully, tying it very closely to the real deep level of understanding. The second chapter, chapter 5, is much more about how and why things function. So there's a little bit of quantum comes into it, quantum understanding and things like that. So basic idea is, what we did in class is we looked at a couple of models, thought what's good about them, what's bad about them, and how they work. The little blue people is my favourite model. I think it's a really powerful model. It's a really good learning and understanding model. So here I have my little blue people, the white in this picture. They're leaving the battery is part of it, or the cell, the source of EMF that we'll pick up on, the voltage that pushes the current around. My little blue people, they are carrying energy as they flow, so our flow is the current. We can count how quickly they're flowing. That is what we mean by current, so how many are flowing past every second. As they go through devices like bulbs, okay, in this case signal lamps, as they go through, the little bags are taken off them and chucked out. So this is energy that they're carrying as they flow. In reality, it is them flowing with energy, so they have kinetic energy. But as they flow with their energy, they lose some of it by going through resistances like lamps and like bulbs and resistors. That energy is thrown out, so there is less energy as they carry on, and when they have run out of energy, then they are pulled back by the attraction of the battery to make them go round. Okay, so really, really powerful model. We can change voltages, we can change currents, we can change the effect of putting more or less lamps in the circuit. All of it ties together, but you can't see this, so we have to use the basic ideas of what we can measure. Currents, voltages, and that tells us about what's happening inside. Okay, so let's pick that up, let's dive in. As I say, you should have a basic understanding of series and parallel circuits. I suspect I'll be explaining them in a different way, and that's because of my background. So go into this, we'll look on the 2 crucial things which are actually currents and voltages in series and parallel. Okay, so something very powerful called Kirchhoff's laws. I'll pick up right at the beginning to explain what they're doing, be able to figure it in complex circuits, series and parallel combined, which is your standard circuit, and we're thinking about where it ends up. I want to avoid that word in answers because it really doesn't help. It doesn't explain clearly. So we are not going to share anything except my knowledge with you. Right, so going into the first section. The definitions are really important, and the definitions are getting clear in your head what these things are. If you can match them to the model, then you can visualize what's happening as well. And this is really, really important, I think, to understanding electricity. Can you see where it's going? Can you see in your mind where it's flowing? So, key, if we go back to SI units, the SI unit for electricity, there's only one, is current. And the key reason is current is the link between everything else. It's that flow of energy. It is a way in which energy is transferred from one place to another. So again, back to our picture, we have a store. In this case, if we have a cell, we've got a chemical store of energy. We've got lamps that need to get hot so they can glow, or other devices need energy in some way. Current is what transfers that energy, takes that energy round to deliver it where it's needed. Okay, and they don't purposely go off to those, but as they flow, as they go through devices, some of that energy will be transferred. So every time they go through something, being plugged into a circuit, whatever it is, including ammeters and voltmeters, it will take some of their energy. So crux ideas for the topic. Really, really important, both in terms of understanding, but in the end it's all about energy. So let's start off. The big one then is current. Okay, and I have a model that runs through, so we'll get on to that about school corridors and things. So firstly, current is ... Firstly signified by I. I've no idea why it is I, even as an electronic engineer. I just happen to be a convenient leftover letter. So current is the rate, that's very important, the rate of flow of charge. Okay, and that's our basic idea. We talk about charge carriers, charged objects that flow. It's not just electrons. Okay, in electrolysis, for example, positive ions, negative ions. Okay, so in gases and liquids it's different. It doesn't have to have wires. It's just that flow, that charge that is flowing about. And the important bit is how quickly it's flowing. So I will put here that it's mainly electrons. Okay. If you want to mix it up, you can think delocalized electrons, but actually that's not quite correct. But if it works for you, go with it. But it's some sort of free electrons, free moving electrons. They are free to move around. They are not captured. They're not the ones held in within the structure of an atom. Okay, so it can mainly electrons, but can be positive, so I use that quite a lot, plus VE, and negative ions. Okay, so if they're free to move, which basically means in fluids. And a fluid for us, liquids, gases, plasmas, which are very much charged, etc. So anything but a solid, basically. So what that is equivalent to, okay, so that's 3 bars rather than equal sign, 3 bars rather than 2, means it's equivalent to number of charge carriers per second. Okay, so that's quite a convenient way of thinking it. Number of charges per second, number of electrons, but the charge of each electron is not plus or minus 1. Just be wary, chemists. So not minus 1, it's actually 1.6 times 10 to the minus 19, as we use over and over. So effectively, the analogy of a school works quite well. Year 7 students, tiny little students, you know, they're tiny. We remember they're tiny. They run around, they rush around. They are not themselves a current. But if you're looking along a corridor, all you can see is this surging of year 7s as they run along. They are going to be on their way to catch sweets. I know that healthy school status, you're not allowed that, but if you had a sweet shop in schools in the old days, they're surging along carrying their sweets with them. They're carrying their bags of sweets. The sweets refer to the energy. So they're carrying their bags of energy as they flow. As I said, each person is basically an electron, but they don't carry one sweet, of course, they carry a bag of sweets. So lots of sweets. So, unit of it, ampere. Monsieur Ampere was French. I should say it is E graph if you really want to get into detail, but it's amps for short. A lot of the research was done in France originally. So they are all French units, ampere, coulomb, after the Prince de Coulomb, and Voltaire, you may have heard of in literature. Charge, go back to that, is a quantum value, okay, a quantum level of something, property. So it's a quantum unit of charge. And that quantum unit for normally is not what we're talking about. We tend to talk about a coulomb because it's convenient. But a quantum unit of charge is that fundamental value that's in your data book, 10 to the minus 19 coulombs. Okay. Again, positive or negative. Okay. So if we think of this, if it's the rate of flow of these quantum charges, then to make up a current of 1 amp, we need 1 coulomb, 1 unit of charge per second. Think about that idea. So to work on that, as it says in my little model, little model that I use, that basically is therefore 1 ampere is equal to 1 over that. So how many of these add up to 1 coulomb to flow per second? So it is 6.25 million electrons, if it's electrons carrying the charge, electrons per second. So your year 7 running around the school, there's an awful lot of them. Okay, so you can't see individuals, you're just seeing this huge flow of year 7 whizzing along. Okay, so there are billions and billions of them. 6.25 billion. Yeah, big number. Okay, so on the scale, there's nothing wrong with this model, but you've got to amplify the numbers right up. Okay, so we're talking averages most of the time. If we're thinking of individual electrons or individual charged particles, if it's flowing through a fluid, then we can think about the details of each one, but generally we are talking about large numbers. Now, again, like year 7s, they are full of energy, not surprisingly, they're full of sugar from the sweets, but they're whizzing around all over the place. Okay. However, the flow of the charge, so getting around from classroom to classroom, is actually quite slow. So even though they're whizzing along really quickly, they're very random. They have what's called a random walk, and particles behave this random walk. So they'll bounce around all over the place. They'll whiz along in straight lines at a very high speed, but won't actually get along the corridor very fast. Okay, so we have that, but actually overall there is what we call a drift velocity. Okay, now we're assuming they're all moving the same speed. We'll see that resistance changes that a bit, but overall, even though they're going generally very fast between places along the corridor, they have this lower speed. So how slow is this speed? Well, let's have a look back at the ideas. If we go back to the idea of electron volts, well, if we had a typical battery, so a typical cell, I should apologise there. So a cell is typically 1.5 volts, so 1.5 electron volts of energy. Okay, so just like we did with our quantum bit at the time. So what that is equivalent to, if we multiply that by 1.6 times 10 to the minus 19, is that gives us 2.4 times 10 to the minus 19 joules of energy. So it's not a lot. Every charge will gain that much energy. Convenient in electron volts, less convenient number. But if we use the proper version, what we can do is put that into 2.4 times 10 to the minus 19 energy joules equals half mv squared. So that electrical work done, energy given by the battery, turns into kinetic energy. That will give us a velocity for an electron mass. You can check this out, use your data book value, but that gives us a speed of about, surprisingly, 726, using exact value, your maximum value of, I should say, kilometers per second. So electrons move really fast. Okay, in theory. Now I should say that's faster than the speed of light, but 1.5 volt battery makes them go really fast. Maximum value, even if it's a lot less than that, it's still really fast. Sorry, not faster than speed of light. What am I talking about? It's still very fast. But they don't go that fast, and this is where it gets a bit interesting. So on average, they're going a lot slower. So if we have a section of wire here, and let's call it a certain length. So let's call it length L. Okay. Well, if they're moving along that length at a certain speed, there you go. There's our particles, our free electrons. Okay, and they're all moving along at a velocity v. We don't know what that is, but we can work that out. Well, velocity is going to be that length divided by the time it takes to go along. Okay, so speed, distance, time calculation. Now, if we use that, we can think about the speed at which they're travelling, but we need to know actually how many free electrons we've got. So what we've got is something called the charge density. N is charge density. And what that is not the total charge with the protons and neutrons and electrons all put together, but basically free electrons in a metal wire, it'll be electrons. So free electrons per meter cubed. Okay, so if you had a meter by a meter by a meter of copper, your standard wire metal, metal for wire, how many have you got? Okay, so for copper is a large value. We'll go into some examples in the data sheet, but we can work it round and just do the theory today. Which means that if I want the actual number of electrons, okay, then what I need to do is I need to take my number per meter cubed and multiply it by the volume. Okay, so I'll just write in number of electrons in this length of wire. Okay, so it's the charge density multiplied by the volume, which I should say is number times by area times by length, if that's the length and that's the cross-sectional area A. Okay, so cross-section area. Okay, and you will see when we put it all together that obviously the number depends on the area, but also the velocity depends on the area, and this links into when you did the experiment. If you did the experiment for required experiment, the GCSE, of different thicknesses of wire and how it changed resistance. So we'll come back to that, but this is the theory behind it. Mathematically though, what do we get? Well, number of electrons is N times A times L. Now, if we want to find current, so to find current, this is a bit squeezed in, but to find current, we need, current, we need to find how much charge flows, okay, I should say I, there we go, how much charge flows in the amount of time that it flows for. Okay, so total charge is number of electrons multiplied by the charge on each electron, or 1.6 times 10 to the minus 19. Okay, that's going to be over delta T. Okay, so how many per second flowing each charge, number per second flowing multiplied by each charge. So I've got that basic idea. Current is how many electrons are flowing and the charge that they carry each second, but I can work out how many electrons I've got from my formula above. So if I put those two together, what I end up with excuse me, is I will equal big N, which is little n A L times by E, divided by the time it takes. Okay, but simplify it again a bit further. I've got my charge density. Okay, I've got my charged electrons. I can look both those up. That's a value for a material. So copper has a certain value, carbon has a different value, for example. And the cross-sectional area is our wire. We have our charge, but I've got length and time, and I've got over here length and time. So, but V equals length over time. So what I can end up with is the current equals, substitute for those, NAVE. and that is in your data book, and this is called the drift velocity equation. So for V equals drift velocity, because when you put the numbers in, if you want to rearrange for V and you put in a typical current in a typical Y, as we'll show in the lesson, this V is a few millimeters every second. So we've gone from the theoretical speed at which they're moving with the battery of hundreds of kilometers a second down to actually a few millimeters a second. And that's because of this fact that they're actually randomly running, if they're year 7s, but electrons are moving around at high speed in random directions. So overall, how they move along the wire is actually really slow. And what I've done is I've recorded a video. It's very difficult to show in class because it's so small, but I've recorded a video of ions, so you can see the coloured ions moving when I turn actually a really high voltage on. So it's a reasonable current, but the speed at which they're moving apart is incredibly slow. Okay, so current can be really big, hundreds of amps and so on. Pretty rare to be that value usually, because that will kill people, but hundreds of amps, but the speed is actually quite a slow drift. Now if you turn off a switch, for example in the room, they go off very quickly because it's not about the speed at which each charge moves, it's the flow of all of them. So if you put a break in a circuit, if you put a switch in, they all have to stop. So it's not about leaving the battery going all the way around, it's the movement of all of those millions of charges, sorry, billions of charges, billions of charges going around. They all look the same, so it doesn't matter how which electron is going through the wire carrying energy, it's how many in total are going through each second. Okay, so how quickly the quantity moves. So yeah, the quantities, the speeds don't have to be high. Right, the other important idea is voltage. It won't work without a battery. Okay, and it's a bit like water flowing downhill. If you don't have that hill, you don't have anything to give it the energy, it won't work. So, changing the height of the hill, the steepness of the hill, we get faster flowing liquids, okay, if it's a pipe. So, at a simple level, is actually quite a deep level, is it's the energy given to each of the charges individually, but again, because there's so many of them, we're going to say to each coulomb of charge. Notice the given to, that's the important bit. So it's given to the coulomb of charge, basically by one of two methods, by a chemical reaction. In other words, a battery and cell, okay, in a cell. And we'll look into the difference. So a cell is basically one pair of electrodes as you draw. So that is a cell. If you have lots of them, it's called a battery of cells, shortened to battery. So where you've got lots of them, you've technically it becomes a battery. So either by that or the only other way, well, there is, you can use heat and chemical reactions of metals. Just by putting metals together you get a voltage, which is why you get rusting if you're not careful. But the main method is either by a battery or a generator, and that's where we use magnetic induction, which you did a little bit of in a GCSE, in a generator, or dynamo, which is basically the same thing-ish. Okay, so for this idea, it's how much energy is given to each coulomb. So each year 7, how many sweets they are given. So the more sweets they're given, the faster they tend to flow towards the shop to fill up their sweets. Okay, so they're going to go quicker if you have a bigger voltage. Now, you may not have heard that term at GCSE, but this is one of the two types of voltage. Okay, the symbol for this is a curly epsilon, looks a bit like a curly E, and it stands for EMF, electromotive force. It's the force that motivates the electrons to move. So it's the energy given to each set of electrons as they fly around, so each few million of electrons. Okay, so given to, i.e. this is where your energy for your circuit's coming from. The other voltage is taking energy away from them. Okay, so energy givers and energy takers. The original source, where they end up. So, how does the rest work? Well, the other bits that link in are kind of a bit more obvious. Resistance, I'm sure you did at university, GCSE at school, is that it's basically opposition. So as the electrons flow, as the charge carriers flow, they'll collide with things, and as they collide, they slow down. Okay, they lose energy. In my model here, they have their bags of sweets taken off them. Okay, so somebody, that's the cruel year 11 rugby players blocking the corridor. Okay, they get in the way, they slow down the flow of charge, and they do that by taking away their energy. Okay, so again, like taking sweets off the little year 7s, so whizzing around, hundreds of rounds, you take their energy from them. So this is a physical opposition. There are other ways of slowing down the charges using electricity and magnetism, but basically resistance is fairly obvious. It's the physical, and that's the crucial bit, physical opposition to moving, and again I'll keep it general, charge carriers, don't have to be electrons. Why? Due to collisions. Okay, that's why it's physical. It is literally a collision, and because of that collision, they come out slower than they went in. They've lost some of their energy, whether they're electrons or not. Okay, so yeah, due to collisions with, and this needs to be correct, the ions, so don't say atoms, the ions in the material, of the material. Okay, why are they ions? Because some of their electrons are free, so it's leaving behind charged atoms inside. So it's the ions that are actually stuck in the lattice, in the structure, that just sit there in the way. Okay, just like year 11s, who are a bit slow and just don't really move around much. So that physical opposition takes energy. So instead of energy given to each coulomb of charge, the millions of year 7s, it's energy taken from each charge. Okay, so that is also measured in the same way. It's also measured in volts, so we'll often call it a voltage, but that's really bad, you know. It's not a phrase really, but it's a general phrase that we can talk about. But it's energy taken from each charge carrier. Each coulomb. So again, same definition, but not given to, it's taken from each coulomb of charge. Why? Because of the resistance. So due to resistance. So anywhere you have resistance, you will get voltage, because it's taking some of their energy. It does it by default. There's no ifs or buts about it. Every time you put something that resists, it will have to take the energy to resist. It's work done. Force stopping them transfers energy. So, excuse me. What it's effectively doing, which is where the phrase comes from, is it's taking away some of the potential energy. It gets a little bit worried, but basically they will have more energy before than they do afterwards. So when you're trying to measure voltage, you're finding the difference between them, and that's why you put the voltmeter across before, before and after a bulb, for example, and you're seeing energy there compared to energy there. The difference is your PD. Okay, we're going to talk PD quite a lot. Right, I'm just getting a warning that my computer is about to restart. So I'm just going to snooze that a second. Yeah, I'm going to do that, and I'm going to have to stop in a fairly short time. Okay, so luckily we're right at the end of that. It's Friday afternoon when they do the computer updates. So we can take those descriptions and we can work them into equations, and these three fundamental equations really link them together. So as I've already shown you, current is the rate of flow of charge. So it is, rather than amount of charge per second, it's more correct to say rate of flow, so dq by dt, differentiation. So at that moment in time, the current is how much that's flowing past, the rate at which it flows past. EMF, okay, that I'm going to kind of give you the idea, I'm going to use it as an E, but you could actually equally, because for voltage, you could talk about a V there. So again, it's a little bit varied. You've got both in your data sheet, but it's the work done per coulomb of charge. So how much energy is given to or taken from each coulomb of charge. Okay, so again, the description is the important bit, okay, for each of those. Sorry, that one up there and so on. And if you've got that description clear, it's summed up in that equation. So you can use the equation to go, energy per charge. Okay. And then the last one, as I say, you could put V equals over Q, taken out, but the crucial bit is the energy is taken out because of the resistance. So how much does the resistance give us that voltage? Well, when you've got that, excuse me, the resistance, well, it's all about how much energy it takes from the flowing current. So it's V equals IR, the daddy of equations that for electric circuits, that's going to appear in every single thing that you do. So V equals IR, resistance is voltage needed to get a certain size current, or voltage produced as you take energy per current. If you double the current, you will lose twice the energy. Okay, so we can link them together in terms of ideas. So really three very powerful equations. All of electric circuits is about those three ideas. Rate of flow of things carrying the energy, how much energy each one is given. Okay, so how big the bags of sweets are, how much big the bags of energy are, how quickly the year 7 are running along with them, and then how much is stolen off them, depending how resistive your year 11s are. If you've got one who's very, very resistive, a very good blocker, shall we say, then he's going to get a lot of voltage, a lot of energy from the little sweets as they run past. Okay, and it will affect the rate at which they're flowing. So they all keep linking back to each other. Okay, so really fundamental lesson. Make sure you're happy with that. We'll go into the kind of more basic fact-like stuff, but this first section is really fundamentally important stuff. Modeling the concepts, use the model, relate the model that you visualize in your head to descriptions, how quickly they're flowing, how full their bags are, and that will link us, and how much is stolen from them, I should say. Don't forget the year 11s. Those three ideas lead to everything. Okay, so make sure you really understand this model, the descriptions, little bit of extra because it's a convenient place to put it with drift velocity, but really make sure you've got those kind of key concepts there and link them to those three equations. We're going to use those over and over and over again.